So looking over here, when we don't have a sound coming through, there's no sound here, nothing is going on, no movement of the tympanic membrane, nothing is coming through, we're going to see the organ of Corti, the cochlear duct is going to be in that still position. The operating point for it is going to be around the 0. So we're going to see those stereocilia standing still. They're not moving either one way or the other. However, if we have the rarefaction component hitting the eardrum, so we're starting over here, rarefaction, that means there's a drop in pressure. And when there's a drop in pressure over here, that means the pressure over here is going to be larger and the eardrum is going to be pulled out. When the eardrum is pulled out, pulling on the ossicles, it is going to pull on the oval window as well. And pulling on the oval window, what's going to happen? Now we know the scala vestibuli and the scala tympani are connected through the fluid, through the helicotrema. And what's happening when we pull the oval window membrane out, it is going to decrease the pressure in the scala vestibuli, which makes the pressure in the scala tympani a little higher. And as a result, that cochlear duct is going to move up. So with the movement up, the basilar membrane is pushed up. What's going to happen? The tictorial membrane is going to shear against the stereocilia for those outer hair cells, pushing them in this direction. If we want to try to get some visualization, this is where the stria vascularis is. This is where the modulus is. This is the inner hair cells. So when the stereocilia is sheared toward this direction, those mid channels, those mechanoelectrical transduction channels are going to open, and potassium is going to rush in to depolarize the hair cells. Now, as we know, there is going to be a rarefaction and there is going to be a condensation, so the other part of the wave. So when the condensation is sent through, we're increasing the pressure, we're pushing on the eardrum, it's going to push on the oval window membrane, and as a result, it's going to increase the pressure in the scala vestibuli. Now the pressure over here is larger than the pressure down here, and what's going to happen to that structure? It's going to be pushed down. Pushing it down, it is the tictorial membrane again is going to shear against those stereocilia, and they're going to be sheared in this direction, so toward the modulus, as we mentioned. And this motion by itself is going to close those mid channels, and no potassium will be allowed in. So generally, when we have the mid channels opening and closing, they're going to cause depolarization and repolarization or hyperpolarization of the cell. So either the cell is going to lose its negative charge or it's going to regain its negative charge. So in this example over here, it is showing us, for example, when the stereocilia is moved in one direction, we are seeing the rush of potassium. When they move in the other direction, we don't really, or that rush stops. The movement of those stereocilia, when they're moved toward, as we mentioned, the stria vascularis, toward the lateral wall of the cochlea, they're going to open. That's going to be an excitatory motion. That's going to open the channels for potassium to go through, versus when the stereocilia is pushed in the other direction, that's going to close all these channels. It's going to be an inhibitory, so no potassium is going to be allowed in. With the excitation, the hair cell is going to depolarize because it has a negative 70 millivolt charge. And then when all the potassium rushes in, potassium is a positive charge, it is going to decrease the potential for the outer hair cell. On the other side, with the inhibition, when the channels are closed, no potassium coming through, the hair cell is going to start dumping the potassium that came in, trying to repolarize and regain its negative potential. Now, as we kind of mentioned a little bit talking about the potassium. Potassium is the major driver ion for depolarization or our sense of hearing. And the endolymph is pretty rich with potassium. The endolymph has a charge of about positive 80 millivolts. So that fluid over here has a charge of 80 millivolts. The hair cell has a voltage of negative 70 millivolt. So that's about 150 millivolts difference, which leads to, as soon as those channels open, it leads the potassium to rushes in pretty good amount into the hair cell to depolarize it. When the stereocilia is sheared and the excitatory motion, potassium comes in, but when the stereocilia is sheared in the other direction or inhibitory motion, they're going to close and no potassium allowed in. Now, there is also calcium that's going to come through, but the major driver is that potassium current. Now, when the potassium gets into the cell, when the cell is depolarized, we have channels over here, those calcium channels. Those calcium channels are voltage activated. So when the hair cell is depolarized, they're going to open. And they're going to allow a large or a rush of calcium into the hair cell. And the rush of the calcium is going to have two important jobs inside the hair cell. The first one is it plays a big role in guiding the vesicles, the neurotransmitters vesicles, all the way to the synaptic region to be released. And it activates the potassium channels on the sides of the hair cells that is going to allow the potassium to leave the cell and the hair cell to regain its potential. Just to avoid any confusion, this is, we're looking over here at an inner hair cell. Inner hair cells have a negative 40 millivolts charge. So when the stereocilia is excited, moved, and the excitatory motion, potassium rushes in, depolarizes the cell. It's not going to stay depolarized. The calcium is going to help opening those channels to basically try to dump potassium out of the cell into that area around it through the space of null and into the Corti lymph. And the goal is to regain that negative potential for the hair cell to get it ready again to be stimulated with the next cycle that's going to come through. Now, outer hair cells, they have an interesting function. They have a feature called electromotility, which is their capability to change their length to do basically their job. So as a result of that electromotility, those outer hair cells are able to do their job of frequency selectivity. So if we're looking at this graph over here, this is, I believe, from guinea pigs. This is the tuning curve. So what they were doing, basically, they were measuring vibration of the basilar membrane as a result of presenting different stimuli. And they were focusing at this point on the basilar membrane. So for example, that frequency that's associated with that region of the basilar membrane, close to about 18,000 hertz, it only needed 15 dB to make that vibrate. Now, what happens when those animals died, so these are measurements that were done post-mortem, that peak, that interesting peak happening over here is gone. So we're still trying to measure from this area on the basilar membrane, but we don't have that frequency selectivity anymore. That electromotility is also important for amplification. So it helps amplifying softer sounds up to about 40 to 60 dB. So if we go ahead actually and look at that over here, the threshold over here is around 15 dB. And when those hair cells are not working anymore, it is close to about 60 dB. So that's about 45 dB loss that happen because of the outer hair cells are not doing their job. Some more recent research, and those studies were done on measuring vibration of the basilar membrane, but more recent research looking at the vibration of the reticular lamina, it shows that the reticular lamina vibrates at a rate of about 6 times faster than the basilar membrane, especially around the characteristic frequency and for soft levels, which is again as a result of that electromotility, as a result of the contraction, elongation that's happening pretty fast by the outer hair cells. Now, how does it all work? How does the electromotility work? When we have the signal coming through, we have the rarefaction component coming through. It is going to depolarize the cell. The steer cell is going to be pushed in the excitatory motion. As a result, potassium is going to go into the hair cell, and it is going to contract the outer hair cell. As the cycle continues, we're regaining a little bit, we're going back to our 0 point, and then as we're going to condensation, no potassium is allowed in, the hair cell is bleeding more of that potassium, it's regaining its negative potential, hyperpolarizing. As a result, the hair cell is going to elongate. So the hair cells, when they're depolarized, they contract. When they are hyperpolarizing, they elongate. As we mentioned, the protein that's responsible for this is called the pristin. Pristin is a protein that is, it uses chloride, the anion chloride, as a voltage sensor. So going back to the basics, when we have a positive charge coming in, it is going to attract negative charge to it. There's going to be an attraction. So chloride is going to be attracted and moved by pristin to the inner side of the plasma membrane. And as this happens, the hair cell is going to contract. When the hair cell starts regaining its negative potential, it is that the chloride is going to be basically pushed away. And as a result, the pristin is going to move that chloride more toward the extracellular side of the plasma membrane. And as a result of that, the outer hair cell is going to elongate. One of the studies that looked at the role of chloride and how it is helpful for those hair cells and found that it is basically the one used mostly because of removal of chloride from the hair cell caused a reversible hearing loss. So when the chloride was allowed back in, allowed for the hair cell to regain its function. So let's look at those little demonstrations. Over here, this is an outer hair cell that does not have electromotility. So we're seeing that movement back and forth as a result of the shearing force. There is no changes to the length of the outer hair cell. There is that movement that's going on for the whole organ of Corti.